welcome to Uncurriculum with Professor Namya. I'll be using text-to-speech conversion for now, since I have my PhD coursework exam coming up next month.
Before we jump into parallel computing, let's quickly refresh our basics. What actually makes a CPU faster? Longer clock period. This slows things down because each cycle takes longer. Increased clock frequency, yes. Higher frequency means more cycles per second. More work per cycle, absolutely. If the CPU can do more in a single tick, you get more done. Increase hard disk. This won't boost CPU speed. It's about storage capacity. Increase RAM helps reduce delays from slow memory but doesn't directly change CPU speed. Increase transistor count. More transistors usually mean more features and more parallelism. Increase data bus width. Yes, it moves more data per cycle. Increase address bus width, not faster by itself, but it lets you access more memory. Pipeline, big yes. Pipelining keeps the CPU stages busy and increases throughput. So the real CPU boosters? Higher frequency, more work per cycle, more transistors, wider buses, and pipelining. Now, why do we even need parallel programming? It's simple. We have a growing need for performance. Data is bigger, problems are more complex, and users expect instant results. Sequential computing, where tasks run one after the other, has physical limits. You can't keep increasing clock speed forever. That's where parallelism comes in, the idea of splitting a problem into smaller tasks and running them at the same time. This is the future of computing. Parallel systems are the backbone of high-performance computing. When you learn parallel computing, you gain skills to design and analyze algorithms that run on multiple cores, debug and optimize them for efficiency, benchmark performance so you can measure real improvements. From artificial intelligence to weather simulation, parallel computing powers today's biggest innovations. But here's the catch. Just because you have a multi-core processor doesn't mean your programs automatically run faster. Legacy single-core programs can't use extra cores. Running multiple copies of the same program is not the same as parallel execution. And converting a serial program into a parallel one isn't easy. You often need a completely new algorithm. For example, if you want to calculate a global sum across multiple cores, you have to carefully coordinate the process to avoid bottlenecks. Let's take a simple summation example. In the original version, the loop is fixed from 0 to n, with simple variable names like I, x, and sum, clean and short. In the modified version, we add flexibility, custom start and end points, custom variable prefixes, and descriptive naming. The trade-off? The modified version is more verbose but better for complex patterns, while the original is perfect for standard loops. Finally, let's see parallelism in action. Imagine each CPU core starts with a number. In the first step, cores pair up and add their numbers. Next, the results are combined again and again until we get a single final sum. This tree-based approach drastically reduces total time because multiple additions happen in parallel at each stage, instead of one by one. And that's our introduction to parallel computing, why it matters, what makes it powerful, and how simple concepts like pipelining and tree-based summation speed things up. In our next session, we'll dive deeper into actual parallel programming code examples, so you can start building your own high-performance programs. Thanks for watching. Don't forget to like, share, and subscribe for more tech deep dives. See you next time.